We are going to talk about the LU factorization. In linear algebra, we want to take a input matrix A and factor it into two matrices. And the product of that two matrices, they will actually get back to A. So, and the L stands for the lower triangular matrix, and the U stands for the upper triangular matrix. So for the zeros just means they're all zeros in here. And I want to talk about why we need the LU factorization. REF in MATLAB, or just do a regular Gaussian elimination, we can solve a system such as AX equals to B. Why do we actually need the LU factorization? So the reason is that if we do Gaussian elimination for A is n by n, and for a B which is n by 1. So if I want to solve this system, it takes approximately order of n cubed time. So if n is quite small, for example 10 or maybe 10,000, that might be still quite doable. But as n goes to infinity, this term will kind of explode. So it will be better if we have other algorithms that give us, for instance, n square complexity to solve this system. And that's the reason we want the LU factorization. How can we use the LU factorization to reduce the complexity just for solving this linear system? Here's the trick. So because A is equals to L and U, and I will show that this actually takes n cubed time to do that. But let's just assume I can factor A into L and U in n cubed time. So if I'm able to do that, and I want to solve the system AX equals to B, because A equals to L times U, I can let U AX equals to B. I just plug these things in here. Then I got this. And notice that the system now becomes this. And if I substitute, I let UX equals to Y, put that back in, I will get Ly equals to B. So this two system basically representing this original system. L is a lower triangular matrix and U is an upper triangular matrix. For either upper triangular or lower triangular matrix, we can solve the system in order of n squared time by back substitution. Remember that in Gaussian elimination, we have two steps, right? So the first step is the forward Gaussian elimination to make A into upper triangular matrix U. For Gaussian elimination, the second step is the back substitution, which is using this U to solve the resulting system. We know that the forward step takes order of cube time, but the backward step only takes order of n squared. So basically, this is a knowledge about the Gaussian elimination algorithm. Right now, what we are doing is that we have A factored into L and U, plug that back into the original system that we want to solve, and then we have this, and formulate it into two little systems. So which means we can do a back substitution in order of n squared. So the first step is to break A into L and U, which require n cubed. So it's still quite not efficient. But the second step is to solve this two little system. So I solve this first. B is already known, and L is from the LU factorization. Then we can solve for Y in order of n squared time. Similarly, after we solve this system, we know what Y is, so they plug that back in and then solve for X. And once we solve X, the original system is solved. So the step 1 take order of n cubed time. The step 2 take order of n squared time. If we do 1 and the 2 step, it's still order of n cubed plus order of n squared, which yields to order of n cubed. But the good thing is, once we factor this step, let A equals to L and U, we can reuse L and U for different B. So for any system AX equals to B, if A is not changing, but we have a change in B, that means we can always reuse the LU factorization result for A. And that's why LU factorization is good for a system that has a change in B's, because we can reuse the A's. Of course, if we only use this algorithm to solve ax equals to b for once, then we don't actually need the LU factorization. But in conclusion, if we need to reuse that many times, then LU factorization can reduce the cost from order of cube to order of n squared.